Okay, good morning. Let's start our second chapter. This is also the second chapter for crystallography, and it is about indexing of crystal. And you can find the content of this chapter in elements of X-ray and diffraction for its chapter 2. And also there are some information from chapter 3 in canisters, material science, and engineering. Okay, and again, let's talk about this. This course is for X-ray diffraction and crystallography. We already talked about the geometry and structures of crystal. So right now we are going to talk about indexing of crystal. And after that, we will start for X-ray diffractions from properties of X-ray, diffraction theories, diffraction intensities, diffraction masses, and the practical applications for SRD analysis. And while we study X-ray diffraction is to explore crystallography. Like this, what we are going to talk about now. And why we study crystallography? Because to explain the properties of materials. Okay, and now let's talk about how we are going to define a lattice point or lattice line or lattice planes. So in this page, let's first try to specify a lattice positions within a unit cell. As we said, unit cell is the smallest repeat in the lattice or in the crystal. So we used unit cells to express a certain lattice positions. And this is what we do for point index. Okay, point index. So let's first define three lattice position coordinates. So for coordinates, we have like a XYZ. And for ABC, it means the unit cell length. And for example, for a cubic, A equals to B equal to C. But when we are talking about the point index, we cannot say that A equals to B equals to C because this is the method. So we cannot assign it to be a cubic structure. It could be any structure from the 7 crystal systems or the 14 Brevis lattices. Okay, and QRS is actually our point index. For example, you see the equations here. Px is actually the locations of the lattice positions, and we use QA to express it. Q here is a fraction length of the unit cell length A, B, C. So Q is for the fraction of A, R is for a fraction for B, and S is the fraction for C. Because QRS is a fraction, so this point index or point indices will be ranging from 0 to 1. Okay, for example, this is a unit cell. We have A, B, and C for their lengths of a unit cell. And then let's try to specify a point index here. For example, this point, this is QRS. And for QRS, we use these equations. So we can write QRS, and then you can see here for the Q means the fraction length of A, and A is for X axis. So here this is QA, this is our origin. So we move from origin for a distance of QA, and then PY is RB. So this is for y-axis. So we move here for RB distance. And Z is for SC. So we move up SC. So we get this point, QRS. Okay, this is how we do to get a point indices. So now, here, QRS is our point index or point indices. But for this point index, it is no need to use commas and brackets. So for example, we have QRS. This is correct. But QRS, this is not correct. We don't need commas. And for brackets, for example, like this, QRS, this is also wrong. Okay, let's see some example. So the first one, for the unit cell shown in the sketch A, this one. Try to locate the point having indices 1/4, 1, and 1 second. This is a half. Okay, and this, as we said, the point indices is about a fraction. It must range from 0 to 1. So if you see a point indices like maybe 1 to 1, then this is wrong. Okay, so this is the fraction. The first one is the fraction for x, the fraction for y, and the fraction for z. So this is our unit cells. And first try to find the origin. Then we can know that the point will be 1/4 for the x-axis. So maybe you can just cut it into 4 pieces. And so on. This is 1, right? So you first go here. And then you got a complete 1 here. And then go for a half. So go for a half, maybe here. That's our result. We check it here. And you can also use these equations because ABC may not be 1, right? So this is the A is 0.48, and B is for 0.46, C is for 0.40. So if you use this equation, you can get the exact point. But if we just need to draw it in this figure, we just use this method from fraction. It's okay. But if we need to write down the exact number, we need to use these equations. Okay, I think this is not hard. And our second question would be specify indices for all number point in a unit cell, as you can see here. So there are 2 types of corrections. First, we give you a point index, then you write it down, you draw it on the paper. The second type of correction is we give you point, and then you tell us the point indices. So this belongs to the second type of the questions. Okay, so we find ninth point here. Then we need to write down the point indices. And for the point indices, as we said, it's about the fractions. So it's not necessary to know the exact number of A, B, or C. We just need to know about the fractions among these three axes. So it's kind of easy. For example, for the first point, usually this is the origin, right? So it's 0, 0, 0. And for point 2, we see that it comes to the edge of this x-axis. So it would be 1, 0, 0. So for 3, 1, 1, 0. And 4 is 0, 0 for x and 1 for y. Okay. And the fifth point will be half, half, half. Okay. You go half, you go half, you go half. And I think you can find the rest of them. 6, 7, 8, and 9. Okay, this is very easy. Very easy. So let's move on to talk about the lines. You can call it the lines or directions. Like a direction index or line index. Okay, so for the definition, we need to define a line, and this line must be between 2 points, because we know that for 1 point is a 0 dimension. A line is a 1 dimension. 1 dimension, we need at least 2 points to make it aligned. And for this directional index, we use vector. Okay, vector. And for different direction, for example, from left to right and from right to left, that will be the same for the magnitude, but the direction would be opposite. Okay, so that's just the concept for a vector. And we have several steps to determine this directional indices. Okay, we write it with UVW with square brackets, and with no commas. Okay, here, square brackets with no commas, UVW. Okay, let's see the steps here. So first, construct a right-hand x, y, z coordinate systems with the origin at unit cell corners. I think we will just assume it to be here, right? For x, y, z, the intercept of x, y, z as the origin. And then, because we are defining a vector, direction indices, so we need to have 2 points. 2 points would be x1, y1, z1, and x2, y2, z2. If the questions tell you 2 points, then you need to use that to get a vector. This is the step 3. We do subtraction from tail point to head point. That is, you use 2 to minus to subtract 1, so you get a result. But most often we use origin point as the tail point, but it is not necessary. It's just let you know that this may not be original origins, but it can also be origins. Okay, and the fourth step will be normalized in terms of lattice parameter. So after we do the subtraction, we normalize it in terms of lattice parameter A, B, C, and length, because this may not be the smallest integer. So we will reduce it to be the smallest integer values. Okay, for example, if you get like this one, we will make it to be 1, 1, 1. Okay, so we need to have an n here. N here is to make these three values become a smallest integer. And as we said for the 0.6, let's talk about a note. If we get a negative index, we will not use -1. We will use a bar instead. So we write it like here. We put a bar above these values. Okay? So, for example, here are three directional indices. So we need to find out 2 points, right? But for the tail point, we use origin. This is O, O, O. And then, for example, this point, what is this point? We need to know it for the point indices. So it would be 1, 0, 0, and the point would be 1, 1, 0. The point would be 1, 1, 1. Then we do the subtraction. For example, like this one, subtraction 1 minus 0, 0 minus 0, 0 minus 0. So we get 1, 0, 0. But this is for point indices. Point indices are fractions. So the actual length would be 1a, 0a, 1a, 0b, and 0c. And then we normalize it in terms of ABC. So we get a result as 1, 0, 0. This is just an example. Okay, let's see some problem here. Determine the indices for the direction shown in the figure. Okay, this is the figure. As I said, we need to have 2 points to determine a line indices or a directional indices, but the tail point is not necessary to be the origin point. So you see here, this is our tail point. This is our head point. So we use these equations. We find out 2 points, head and tail. We first do subtractions. We get a result here. And then normalize it with edge length. And then we make it to be the smallest integer. So after we do the subtraction and the normalize, we get -1, 1, and 1/2, right? but we need to make it to be the smallest integer. So we will write like -2, 2, and 1. That's the answer. Okay, so again, the type of questions could be we give you a drawing. You tell me the directional index, or we give you a directional index, then you draw it for us. But it's the same. You use these equations, and for a directional index, you need to know 2 points, right? So, for example, here we will tell you that at least 1 point, so you can get the drawing here. So the 1 point will be origin. So we know that for x1, y1, and z1 will be 0, 0a, 0b, and 0c. Okay, so let's try to do the calculations. 1 minus 1 and 0. This is our result. 1 minus 1 and 0. Okay, so d2 must be 0c. y2 must be minus 1b. x2 must be 1a. So we need to get for the locations, and the location is 1 and minus 1 and 0. This is the location. So we need to find out this location. This is for the head point. The tail point is here, right? So you need to find the head. So for x, y, z, we first go here for 1x. We go here for a minus 1 y and z for 0. So we have these 2 points from tail to head. This is the answer. Okay, and let's talk about the crystallographical equivalent. Equivalent is in Chinese 等效. Okay, and for some crystal structure, but not all of them, we could have several non-parallel directions. So they have different indices, but actually they are the same in a crystal structure. For example, in the cubic system, we could write down these point indices. You can see that 100 and minus 100, actually they are for a different direction. So as you can see here, 100 is this one, and minus 100 is this direction. Okay, and 010, let's say this is SYZ. 010 is for this, and 0 minus 10, and also 001, and 00 minus 1. So actually, all of these directions are equivalent in a cubic, because for a cubic, A equals to B equals to C, and also alpha equals to beta equals to gamma equals to 90 degrees. So for a cubic system, it shows a very good symmetry. And to simplify it, we can write it down as a family. We call it 100 family. 方向族. Okay, but as we said, not all of the crystal structure will have this relationship. For example, in tetragonal system, we know that A equals to B, not equals to C, and alpha equals to beta equals to gamma equals to 90 degree. And here, 100 and 010 are equivalent because A equals to B. But 100 and 001 are not. 110, as you can see here, is this one. But 001 is this one. They are not the same because A is not equal to C here for tetragonal system. So they are not equivalent. Okay, and here is a note here. If we use square brackets, we know this is the rational index. But for the rational index, actually, we will not write it like this way. We make it to be the smallest integer, right? So actually, these are the same, but we will write it like this one. Just like the rule we have told you. Make it to be the smallest integer. Okay, and let's move on to talk about planes. This is about the planar indexes. So we will use a term like this is Miller indices. Let's see its definitions. So for Miller indices, we define it as the reciprocals 导数 of the fractional intercepts which the plane makes with the axis. It seems complicated and hard to understand, but that's okay. Let's try to see the steps here. I think you will know better. And actually, the first point is important. If the plane is passing through the origin, we move to parallel planes. We can't let the planes have intersections on the origin. Okay, that's the first point. And then we try to identify the intercepts A, B, C. We use capital A, capital B, and capital C for XYZ axis. And then we take reciprocal of these values. So for A, it will become 1 over A. Okay, and here, this is a note. If a plane that parallel an axis, so it will have an infinite intercept. Okay, try to think about it. For example, this is X, Y, and Z. A plane parallel to the axis, let's say this plane. This plane is parallel to X and Y. So you can't find an intercept. So the intercept would be infinite. And then we take reciprocal operations. It will become 0. Okay? This is just a note. We will talk about this. And then after we do the reciprocal of intercepts, we normalize it in terms of A, B, and C here. And then again, that's reduced to the smallest integer. The smallest integer. Then we can get out the result. And here we have A and capital A, right? So for A, B, C, it means the lattice parameters. And for capital A, B, and C, they are for integers. Oh, sorry, intercepts. And how we write it? We write it in the parentheses with no commas, like this one. And also, again, a bar is used to express a negative index. For example, 1, 1, 1. If you want to have a negative 1, write it here. Okay? Okay, let's move on to have some practices for determination of meter indices. And we have 3 different plans. This one is 001 plant, and this is 110 plant. This is 111 plant. Let's try to use this equation and these steps to determine meter indices. So first, let's assume that we have our plans for this one. Let's see that because this plane is on the origin, it has intersect with origin. So we need to relocate the origin or the plant. So it's okay. We can just move this plane. For example, we move above or below so that it won't have intersect with the origin. Let's say we move it here. Okay, and then let's find the intercept. Okay, so this plane has no intersect with x and y axis. Okay, no intercept. It means that the intersect is infinity. Okay, infinity intercept. And then we need to have a reciprocal, right? So this is for intercept, for x, for y, and for z, let's say 1. Okay, so that's for intercepts. And then normalizations. This is just about this one. A, B, and C. Reduction, I think is okay. We don't need to have a reduction. So after that, we can get 001 meter indices. Okay, let's see this one. So this one, we should obtain it as a 110 plant. And let's see, because it didn't show intersect with origin, so it's okay, we can just use it. And let's find the intersect for x, y, and z axis. For x is 1, for y is 1, for z the intersect is infinity. So we can get that 1a, 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 infinity, 1a, sorry, this should be b and c. Okay, so we get 1, 1, 0. Let's see this one. Okay, no intercept with the origin. Find the intercept 1, 1, 1. So I think it's easy. We get 1, 1, 1. Okay, an important concept as we already talked about, if we have a plant, it is parallel to the axis, then we will have an infinite intercept. So infinite intercept for the reciprocal, we get 0 for the index. So for example, you see a 0 here for the x-axis. So you know that this plane will not intersect x-axis. It is parallel to the plane, just like this one. Okay, let's see this example problem 3.10. Try to determine meter indices for the plan shown in figure A. Okay, so let's see the steps. We have a lot of steps, right? And based on these equations. But first, because it passed the origin, so we must move this plan to different locations. You can choose anyone you like. Let's say we choose this. We move it to left. Okay, we move it to left. So let's find all the intercepts for ABC. Okay, intercept for A, no, no. Okay, so intercepts for B is -1. For C is half. So, and we get reciprocal. So we get 0, -1, and 2. So that's our answer. Okay, and let's see these different questions. Construct a 101 plant with this unit cell. Okay, 101 plant. If you have a lot of experience drawing this, it'll be easy for you to draw a plant. But let's first try to go the basic way. That is, we use these equations. So 101 means H is 1, K is O, L is 1. Okay, so how can we get 101? So A would be 1A, and B would be how to get 0. B to be infinity, and C to be 1C. Okay, so these are the intercepts. So for x-axis, intercept is 1. For B intercepts, for B axis, no intercepts. For C intercept is 1. Okay, so it must pass through these two points. And then it cannot touch y-axis, so it will look like this. Okay, so this is the answer. And let's talk about crystallographical equivalent for planes. We already know it for directions, and also it will be the same for the planes. And for atomic packing, it should be different for different planes. But if we have a family of planes, they will have the same packing. So it will be important to identify the equivalence of planes. For example, for cubic systems, like this picture, 111 family of planes contains all of this. Okay, regarding the negative signs, and this is because all of them have the same atomic packing. But for tetragonal, if A is involved with C, because A equals to B, not equals to C for tetragonal system. So for example, for 100 families, it contains 100, 010, and also the negative one. But 001 is not equivalent with the 100. Okay? And this slide shows the despacing of planes. And actually, despacing means you can first have a look for this 3D view. Okay, so let's see that. This is the 100 plane, right? 100 planes. This is a 100 planes. And after a D-spacing, we will see another 100 plane. So this is the spacing. We call it D-spacing. And for 200, all of these are 200 planes. So it has its 200 plane has its D-spacing. And there is a very important concept, that is, with a larger index of planes, it will have a smaller D-spacing. You can see here, this is 100, this is 200. With a larger index, like this one, it shows a smaller D-spacing. This is because the reciprocal operations of the fractional intercepts. For example, for 100, you see here how to get 1 for h. So it means that a equals to 1a, but how to get 2 here? So a prime would be a half a. So after the reciprocal operations, it will become 2, right? So that's why a larger index of plane have a smaller D-spacing. Okay, and you can also see the D-spacings of planes in a 2D views. I think you will figure out that for different plane, for different indices, they show different D-spacings. Okay, and right now let's move on to talk about indexing in the hexagonal system. Because hexagonal system is a kind of complicated. It can have 3 axes, 3 index systems, and also 4 axis systems. For example, right now we already know about UVW. And for hexagonal system, we can use UVTW. As you can see here, B is for 3 axis systems, A1, A2, and Z. Okay, and here we can use A1, A2, A3, and Z. This is the extra one. This is the extra one. Okay, so in general, we first do UVW, and then we can have equations. We can convert UVW capital 1 to UVTW. We use these equations. Okay, so you need to remember so that you can know how to convert it. And here for T, you can see that T is actually minus U plus V. So once we know U and V, we can get T here. So sometimes T can be replaced by a dot here. Okay. And let's do some practices. So first, as we said, we first do 3 axis system and then convert it to the 4th one. So first, we have an example. This is A1, right? A1, this direction means 100, and this A2 is 010. This is direction, not plane. And this Z is 001. Let's see that how to get this into this 4 axis. So 100, we use this. So 1/3 2u minus v, 2u minus v, so 2. And 1/3, 3, 1/3, right? 1/3, 2v minus u, 2, 0, minus 1, so minus 1. And t equals to minus the sum of this. So it would be minus 1. W equals to W, that's this z, 0. So after making this smallest integers, we get 2, minus 1, minus 1, 0. Okay, I think these three are very similar. Let's try to do this. 1, 1, 0, which is 1, 1, 0, okay? This one. It is between 1, 0, 0 and 0, 1, 0. This is a vector, right? So 1, 1, 0 will become one third 2u minus v, so it's 2 minus 1. And 1/3 2v minus u, similar. 1/3, and this is minus the sum of this. So this is 1, this is 1, it will be 2, but with a minus sign. And w is the same as 0. So it will be 1, 1, minus 2, 0. Okay, and for 1 minus 1, 0, 1 minus 1, 0 is this point. How to get it? Because this is 1, right? This is 1. 1, 0, 0. How about this one? This one is 0 minus 1, 0. 0 minus 1, 0. And this one is in the middle between these two. So just the sum of this. 1 minus 1, 0. How about this one? Opposites of this one, right? So minus 1, minus 1, 0. Okay, you can make some practice for this. Let's see some example. Okay, so we have a direction here. Determine the directional indices for 3-axis coordinate systems. So 3 axes. Okay, so I think you can use these equations as we know, because we need to do subtraction, right, from tail to head. This is the origin for 3 axes, so it's 0, 0, 0. This is a point indices, and this one is 0, minus 1, and half. Okay, do the subtractions. So this is a 0, 0, 0, and this is 0, 8, minus 1, B, a half, C. So let's try to see the result here. 0, minus 1, a half. But we need to use n to make this value the smallest integer. So it will be 0, minus 2, 1 for the directions. Okay? Okay. So we have 0, minus 2, 1. And for B questions, ask us to convert these indices into 4-axis one. Okay, so use these equations. 1/3 2u minus v, 2u minus v, 2. 1/3 2v minus u, 1/3. Sorry, no. Now 1/3. This is just minus sum of these two. So this 2, it would be minus 2/3 over 3. And negative sign, so 2. And then w equals to w, it will be 1. So make it the smallest integer. So it will be 2, minus 4, 2, and 3. That's the answer. Okay, after knowing how to see this indexing in hexagonal for direction, let's see for planes. And we call it, this is a meter Brevis coordination system, HKIL. So we know HKL, right? For a four index system, we add I here. And I equals to minus H plus K. So all of these are the same. We have an extra point here for hexagonal systems. I equals to minus H plus K. Okay, we can see some example for here. For example, this is what we call basal plane. It's 10001. How to see so? Okay, so we need to find the intercepts, right? We first move it here. And then see the intercepts with A1, A2, and A3. So there is no intercepts. So it will be O, O, O. And for Z, just one. Okay, and this is what we call pyramidal plane. So intercepts with A1 will be 1. Intersections with A2 actually should be here. Okay, should be here. No interceptions, so zeros. And for this one, this is I, right? I equals to minus H plus K, so minus 1. For Z, this one should be 1. Okay? And for prismatic with A1, it should be 1. Oh, sorry, minus 1. And for A2, it's parallel to it. So, infinity, we get 0. And I equals to minus H plus K, so it will be 1. And for Z axis, also parallel to it, so it's 0. Okay, so this is practice for this plans. And let's see this example problem. Determine the meter Brevis indices for the plan here. Okay, use these equations for H, K, and L. Use this one for I. So we can get H, K, I, L. Okay, so first try to get H. Intersection 1. And for A2, intersection should be here, minus 1. And for I, minus the sum of these two, so it would be 1. And for L is Z, right? Here. Oh, sorry, the sum of these two, this should be 0. And for Z is also 1. So we get 1 minus 1, 0, 1. Okay, here are some supplementary to indexing in hexagonal systems. As we said, we have a different plane, right? We have basal plane. This is what we call 基底面. 0001 is called basal plane, and 1 minus 100 is called prismatic. You can see here. Okay, basal plane, prismatic, and pyramidal. For 1, 0, minus 1, 1. And there's a circle here. You can see here. It says that S3 is 1 minus 1. This is wrong. I think it's a typo. it should be -1, -1, and 0. Okay, so for three for three axis systems, the A3 one should be this one. Of course, for three axis system, there is only A1, A2, and Z. There is no A3. Okay, so this is just supplementary material. And this is a summarized table for crystallographic indexes. So we have points QR, we have a points QRS, directions UVW, and also we have non-hexagonal one and hexagonal one. So UVW, UVTW. For hexagonal one, we have two ways to express it. And for planes, non-hexagonal, HKL, hexagonal, HKIL, HKIL. And here are the definitions. For example, for a plant, our direction, for direction we use square brackets. And for plane, we use this one. For family, and for plants, okay, just a summarized table. And then right now we know how to make indexings. For example, for point positions in the unit cells. And then let's try to see that for different crystal structures. Let's start from simple cubic. Simple cubic is actually primitive. It means that there is only one lattice site per unit cell. So all the atoms are at the corners. So it's corner atoms. And let's say we have one on its origins, that is 000. Okay, and we can label it for all the atoms at the corners. And actually, all of these corner atoms can be simplified into a 000 location. Okay, you can choose left. We can choose origin for this one, for this one, for this one, right? We can change the origin. Okay, so all the atoms are actually equivalent. So for simple cubic, you just need list lattice positions to describe simple cubic. Okay, let's move on to talk about some for more complicated. Okay, BCC is more complicated. It's a non-primitive cell. So it has two lattice sites per unit cell. So for example, for this atom, we have 8 corner atoms and 1 interior atoms. So for corner atoms, just like simple cubic, we can simplify it into 000 lattice position. But for its interior atoms, it will be a half, half, and a half. And it is worth mentioning that actually the 8 corner atoms and the interior atoms are the same, but for us to use point indices to talk about these points, we must first define an origin. For example, we define this origin, then we will know that these are corner atoms. So we need to classify them. Once we have an origin, we can classify it into this by two. One is corner atoms, the other is interior. So this is that we must pay attention. Okay, all of them should be the same, but considering writing out these lattice positions, body center and corner would have different locations. And let's see for FCC is also non-primitive. Sorry, this should be face center. Okay, so we have 8 corner atoms and 6 face atoms here. But let me say that these 8 corner atoms must be shared with the other unit cells. Okay, so we can try to use this point indices for this 8 points and this 6 face atoms. So after writing all of this, we can simplify them into 4 groups: corner atom, face atom 1, face atom 2, and face atom 3. So for example, this one and this one would be simplified as 1. This one and this one would be simplified as the second one. And then this one and this one will be simplified as the third one. Okay? Because they are different if we consider for equivalences. So we have 4 for this face center cubic. And this slide shows the D-spacing in crystal systems. I think we already talked about D-spacing. For example, this is 001 plane. This is also 001 plane. There is a D-spacing here. Length. This is for cubic, right? It looks like a cubic, but for different crystal systems, as you can see here, the D-spacing have, for different crystal systems, the D-spacing have different equations. For example, for cubic, we use these equations. This is the meter indices. This is the length for the unit cell for this cubic. So DHKLO can get this spacings. Okay, so this is just for your information. And also, we have something to tell you, but not in this chapter. Structure factors. That means not all planes will be shown. For example, this is a crystal structure. We know that, for example, we could have 111 or maybe 222, but actually, because of the structure factors, some of it will not be shown. For example, using the XRD experiment. Okay, so we will just talk about it in the following chapters. Okay, let's see this concepts checked. 3.3. So for cubic structure, as the value of the planar HKLO increased, that's the distance between this is about the D-spacing. This is okay. D-spacing will increase or not. So let's just try to write down these equations. And the question is, if we increase HKLO, what will happen to these spacings? So if this value is bigger, this value will be smaller. Okay. And then let's talk about packing and the relationship with energy. So we know that metallic bondings should be non-directional. And non-directional means that there will be less restrictions for atomic packing, right? So it should be dense packing for metallic materials because it will have the lower bond energy to have a smallest neighbor distance. So for example, this is a non-dense structure and a random packing. So let's see that this is the energy and atomic distance profile. The point will be here because the R is larger. It could be more stable if it is dense, like this one. So if this is dense, it will go here for the R. So this is the most stable one, right? So the conclusion is the older structure would have minimum in bonding energy and therefore more stable. And for close-packed crystal structure, we know that metals should have a higher packing density. And for FCC and HCP, after the calculation, we get atomic packing factor as the maximum one, that is 0.74. And for BCC, it's 0.68. For simple cubic, will be much more lower. Okay, so close pack means the atoms are closely in touch with everyone. So we could have a maximum packing density or planar density because this is a plane. So you can see here, this atom, they are all in touch with each other. And for FCC and HCP, they have a close pack structure. And actually the difference between these two crystal structures is the packing sequence. For example, you see here, this A means a location. Okay, this is a location. And after that, if we try to pack above this atom A, we have two suggestions for B location, like here. Or we can just, sorry. Okay, we can choose B or choose C to stack it here. And for example, for HCP, it's AB, AB, AB stacking sequence. For FCC, it's ABC. You first go A and B, and then not back to A, but to C. Okay, this is for FCC and HCP. And you can see the 3D structure here for HCP, AB, AB stacking. And this is the closed pack plant, which should be 0001 for HCP. This is what we call basal plane. And for FCC, it's a ABC, ABC, like this stacking sequence. So you can also view it from this direction. And this closed pack plane is 111. Okay, and for ceramic structures, they can also have closed packed crystal structure, but it will be more complicated. And actually, for the closed pack planes, because ceramic have anions and cations, but anions are much more larger, okay, because it gains electrons. So for anions, they could have closed pack planes just like this one. And for these cations, it will just fit into the interstitial sites. For example, like tetrahedral or octahedral sites. These are different sites. And also, AB-AB stacking sequence and ABC-ABC stacking sequence could both occur in ceramic materials. And let's see how to estimate linear and planar densities for crystal structure. As we know from previous slide, closed packed plane shows the maximum planar densities because all the atoms are in contact with each other. But let's first go through the linear density. So the definition is the number of atoms for these lines over the length of these lines. And there are two notes here. First, the number should pass through these centers. And the second, we also need to consider atomic sharing. But because this is a linear density, so we view it as a line. For example, we try to calculate the linear density here. Let's see here. How about this length? Okay, this is R, this is 2R, this is R. So the length will be 4R. How about the number of atoms here? So this is one atom. How about this? This should be a half or 1/4. Because this is a line, so we can just see it through these directions. So it should be a half. If this is an area, it will be 1/3 because 1/3 is for this one, right? Or maybe 1/8. So what I'm going to say is, because this is a linear density, you should look it at one-dimensional way. So look it here, it's just like this is one atom. This should be half atom. So the total will be 2 atoms. Okay, and then get a result. And for planar density, actually looks similar. Number of atoms over area. And the number atomic sharing should be considered, but in a 2D view. Okay, let's see here. Let's try to find the area here. So this is R, 2R, R. So this is 4R here. And this one, you should see it it will be more complicated. So this is the plane like here, right? This is in touch, A, B, C, but AD, how about AD? AD is just A, okay? So this is 4R, so we also need to find A and R correlations for FCC. And I think A equals to square root of 2R, so you get it here. But how about the number of atoms? You see here, because we need to consider it in a 2-dimensional view. So for this one, 1/4, a half, 1/4, 1/4, 1/4, a half, right? Okay, so you add all of this, 1/4 for 4 atoms, and a half for 2. This is 1. This is 1. So we got 2 atoms. Okay, let's talk about isotropic and anisotropic. Now we know the crystal structures can be indexing for point, direction, and planes. And actually, the physical properties of materials could depend on its direction or plane. For example, for different directional or planar densities, we could have different materials properties. And if this directionality of properties occurs, is called anisotropic. And if the properties are independent on the direction or planes, it's called isotropic. Okay, so if our material have a very good symmetry, then it will show isotropic. But if the symmetry of crystals is lower, it will show higher anisotropic. This is just an example to tell you that for example, like different metals with different directions. I think this should be planes. It will be more correct. For different planes, it shows different mechanical response to its mechanical property. And let's talk about symmetry. And actually, symmetry is very, very complicated and hard to learn. So in this course, I will just give a very little introduction to the symmetry. So there are several types of symmetries. There are more than these four, but let's just introduce these four. So first, reflection symmetry. It means that there is a plane, we call it mirror plane. Between these mirror planes, there is a symmetry, and the symbol we use M. And the other one is rotation axis symmetry. It means that we have symmetry to a rotation axis. For example, we can say it like a n-fold rotation symmetry. For example, if n is 2, it means that 36 degrees over 2 equals to 180. So after 180 degrees, you will bring it back to itself. And for 3/4, it means after 120 degrees, it will bring you back to itself. And for 2/4, we have a symbol, ellipsed. And for third, triangle. For 4/4, squared. For 6/4, hexagonal. Okay, and then inversion center symmetries is just a point symmetry to a point. And then rotation inversion symmetry is a combination of these two. So you first have a rotations followed by inversion, then you will see the symmetry. Okay, let's see the cube. We know that cubic, one of the 7 crystal systems, has a very higher degree of symmetry. For example, it shows reflection symmetry. We have a mirror plane here. So between this mirror plane, it shows symmetry. And also rotation symmetry. We will have a rotation axis. For example, for this one, this is 4/4. For this one, it's 3/4. For this one, it's 2/4. And then we have inversion symmetry. Inversion symmetry is a point symmetry. So for these points, A1 and A2 are symmetry. And then rotation inversion symmetry. It means that a combination of a rotation axis and an inversion center. For example, A1, you first have a rotation, a 4/4 rotation to A1 prime, and then we will have inversion symmetry to this point. So this one, and this one. So in other words, A1 and A2 have a rotation inversion symmetry. And let's see this at example. So this is what we call point group, 点群. Okay, the first one, 1/4. 1/4 means there is no symmetry. And then 2/4, this is the axis, rotation axis here. So after 180 degree, we see a rotation symmetry. And 3/4, 4/4, 6/4, and then for mirror, this is a mirror plane, right? And this is 2 mm. It means 2/4 and mirror, 2/4 plus mirror. So this is the 2/4, and it will show extra mirror planes. So we have another m, 2 mm. Okay, and this is 4 mm. It means 4/4 and a mirror. But it will also show more mirror planes. So it means that a combined symmetry will produce more mirror planes, just like these two examples. So right now we introduced 8 point groups, and actually there are a total 10 2D types of point group. We still have 3M and 6mm. And also considering a 3D point group, there is 22 types. And also there are space groups. Okay, and these are complicated. We will not introduce in this course. And then let's talk about crystal systems and symmetry. As you may know that for unit cell, we use ABC and alpha, beta, gamma to express it. And then we call it crystal systems. So there are 7 crystal systems, and you can see the minimum symmetry elements for cubic, tetragonal, orthorhombic, and the other one. So this is just for your information. As you can see that cubic has a very higher degree of symmetry. For triclinic, there is non-symmetry. And this is just to let you know that this is the second chapter for crystallography, and no more for that in this class. So this is to let you know that if some subjects we skip in this course, and if you like, you can self-learn more about it for 3D point group and space group. So it can maybe be for you to use in the in-depth crystallographic expressions. And also reciprocal lattice, atmosphere, and zone axis. We skip this part in this course. This could be practical for TM analysis. If you have interest in this, you can take the course for TM. And also, projections. Okay, projections and wavelet. It could be used for crystallography expression and maybe texture analysis. Okay, so that's all for this chapter. Thank you for your attention.